Hey, welcome back to Math with Patrick. Today's July 2nd, and we're solving problem number 183 from the Daily Epsilon calendar. And let's try to figure this out. Honestly, it looks like a bunch of mess, a bunch of letters all here. We have what looks like x times y times z times w times v times 4 is equal to v times w times z times y times x. So all of these variables are just repeated, but in reverse order. Okay, that's kind of strange. And they are all mutually not equal to each other. Well, I mean, technically that's not what that says. Like I could do like 1 is not equal to 2, which is not equal to 1, which is not equal to 2, which is not equal to 1. So there is a way to like kind of fudge the numbers here where maybe there are some variables that are equal to each other, but at least x and y aren't equal to each other, and then y and z, z and w and v. Initially, this just kind of seems weird to me. Like, let's assume for a sec that none of these are equal to 0 for just a moment. Then that would mean that I could divide both sides by these variables. Like, say v was like 3 for a sec. I could divide both sides by 3 and cancel those out. So just under the assumption that none of these variables are 0, then I could just cancel them all, right? There's a v on both sides, w, z, y, and x. So I don't think there's really anything stopping me from dividing both sides by x, y, z, w, v, x, y, z, w, v. And then I'm just left with 4 equals 1. And clearly that's not the case, so something is wrong with my assumptions here. And so maybe I do have to have a 0 somewhere. What's kind of weird is that 0 could be anywhere. So one of those is equal to 0, probably, but then I don't know which one. So maybe I'm not understanding the problem. Give me a sec to think this through. They're digits. I didn't even figure it out. I actually gave up. I was trying like different ways to figure this out. I was still operating under the assumption that these were just numbers. I tried like subtracting both sides by v, w, z, y, x. I did stuff with the zero product property. I talked about how these are in different orders, so maybe the multiplication here isn't commutative. And I couldn't find a solution. I gave up. I talked to my girlfriend, and she was like, wait, are these numbers supposed to be like, and then she said like a random 5-digit number, like 14,420. I forget what she said, but she helped me realize that these were digits, not numbers. So shout out to Marissa. Let's figure this out now. I have a 5-digit number over here, and I multiply it by 4, and I get another 5-digit number. So that does mean that the value of this number is less than this one. And further, it's kind of on the smaller side, right? Because like if I let x to be equal to 3, and then I try multiplying, say, 30,000 by 4, and I know that I can't have copies of the same digit, or at least I can't have y and z being equal to each other, but for the sake of example, trying a number this big times 4 is going to get me 120,000. And then now that's a 6-digit number. That's too big. And so x really can only either be 2, because then I'd get 80,000, and that's okay. Or it could be 1. I think it'd be really silly if x were a 0, because at that point we have like a 4-digit number instead of a 5-digit number. And then why even have 5 digits here? So based on the size of these numbers, we can determine that x is either equal to 1 or x is equal to 2. And fortunately, we're getting on the right track, right? Now we've like narrowed our search space down. There's a 50-50 shot that we're right already. What else could we figure out? Well, if maybe let's look at the other side of things, like maybe this v right here. We could see what happens when we multiply any digit 0 through 9 by 4. So we could do like 0 times 4, that's 0. We could do 1 times 4, that's 4. So clearly we're just kind of counting by our 4s here. So there's 8, 12, 16, 20, 24, 28, 32, 36, and then 40. Although we aren't going to get 40, right? Because that would mean that V has to be equal to 10, and 10 is not a digit, that's a 2-digit number. So I don't really need to consider that one. And looking in my ones place over here, I get an X. And so I need to make sure that once I multiply V by 4, I'm going to get a number that has either a 1 or a 2 in the ones place. And clearly the only option here is when I have a 2 in the ones place. So that actually confirms that X is equal to 2, and we're all done today. Maybe it would be a little bit interesting to see if we can solve for what the rest of the numbers are. So let's try that out. So just by studying the 10,000s digit and the ones digit, we know that X is 2. But we can probably figure out the rest. So let's try it out. Okay, so V has to be one of two different numbers. It's either going to be this one, which is 3 times 4, or this one, which is 8 times 4. So now I have two options for V. Either we have a 3 or we have an 8. And maybe we have to go through the same process to kind of work our way through the number and figure out what W is. So let me make that 2 look more like a 2. It looked kind of like a Z to me. There we go. Close enough. Okay. So what happens when V is... Oh, well, there we go. We already talked about this. If V is 3, it's too small. So V actually has to be equal to 8. So there we go. We're figuring this out. We're getting closer to our answer. Now that we know that V is equal to 8, we could maybe do something with this 8 times 4. That's going to be equal to 32. So then, well, here's the 2 that we already talked about, but this 3 would kind of carry over to the tens place. Let me actually write it out as like long multiplication. Here the Y, Z, and W are still the digits we don't know. And if we multiplied it like this, we would get 32. I'd carry the 3. And then to get this number right here, I do 4W and then plus the 3. So if W were 0, I could just get a 3 right there for Y. If W were the digit 1, then we'd get 7. So here it looks like I'm just counting by 4 again, but offset a little bit. So it could be 3, 7, 11, 15, 19, 23. And I think we're like cycling back up there with our ones digit or ones place. Well, I guess technically it's the tens place since it's here. Ultimately, this is showing me that Y is odd, at least, because I'm not getting any even numbers there in my ones place. So I'll say, Y is odd. I guess we could study what's happening with the Y in this number instead. So if we tried picking a big number for Y, say a 9, we could do like 29,000 times 4. Again, I'm just doing zeros for placeholders for a sec. This number is going to be way too big, right? Because 30 times 4 would give us 120 and then 1,000. And so 29 times 4 would be 116,000. That's a 5-digit number. That's way too big. And then also we need to account for the fact that we have an 8 right here. So even if I picked something like maybe 23,000 times the 4, 23 times 4 is going to be whatever 46 times 2 is. I'm just adding them right now. So it'll be 92,000 when we multiply this one by 4. And so if we put a 3 right there for Y, that would make our V digit too big. So we could put a 2 there maybe. That would be okay, right? 22,000 times 4 does give us 88,000. But we're doubling up on digits. So that means X and Y are the same, and we can't have that. So maybe Y is 1? Yeah, and Y can't be 0 because Y is odd. We already saw that. So Y has to be 1. Okay, that's cool. So let's put a 1 there. Let's put a 1 there. then let me get that list again. We had 3, 7, 11. That could be a candidate number here. 15, 19, 23, 27, 31. So either one of these could be okay. This was when W was 0, W was 1. Here's when W is equal to 2. Then 3, 4, 5, 6, where W is equal to 7. Now, it doesn't necessarily say that X and W have to be different. Like, it probably means that, but I don't certainly read it that way. So maybe W could be 2, maybe W could be 7. And I'm thinking 2 is too small. So now that we know that our small number starts with 21 and then some amount of like numbers over here, if we multiply this by 4, we are surely going to get 84,000 something, or maybe something more than 84,000. And it wouldn't make sense to have a 2 for our W digit right here, because the only time that this could be a 2, and of course we need our number to be bigger than 84,000, the only time that this could be a 2 is if we cycle over to 92,000. So we do need it to be 87,000 something, and that does mean now W is 7. So we are just one digit away from figuring out this puzzle. Maybe we could figure it out by like just rewriting that long multiplication again. 21,000z178 times 4. Let's just see what happens. So here's that 32 again. When we do 4 times 7 plus 3, that's going to be 31. Great. So our 1 lines up right here. For the next one, we need to do 4z plus 3, and that's going to be equal to probably a 2-digit number. And then somehow that needs to kind of match what's going on over here. Well, currently, if we just kind of ignore the fact that we're going to carry a number over, we're going to get 4 times 21, which is 84. But I do need this 4 to be a 7 to match our W digit right there. So for this to be a 7, I must have carried over a 3. And so that must mean that I have a 3 here in like my tens place for whatever this number is. And so let's just kind of count by those 4s again real quick until we reach somewhere in the 30s. Getting there, let's see, so 27, okay, 31, 35, or 39. So here are our candidate numbers for what's going to go here. And then we need, let's see, this is going to be when z is equal to 9. This is when z is equal to 8. This is when z is equal to 7. And I feel like I just need to stare at it until it becomes clear to me. What number should we put here? Well, z is the ones digit right here. So, oh, there it is. I needed z to match the ones digit, and so this is the only pair right here where z matches the ones place of my value that has 3 in the tens place. Whew. All right. Ultimately, that must mean z is equal to 9. There is our number. I'll even replace it right here. And then once we do 4 times 9, 36, plus the 3, that's 39. And then our multiplication is now complete. Wow, that was a fun problem. It stumped me at the start, and then also kind of working through the digits here was fun and challenging. I really appreciated the number puzzle here. Our number is 21,978, or on the other side, it's 87,912. All of our numbers are distinct from each other, so I guess the kind of strong claim here is true, where all of our digits are completely different, and ultimately, x is equal to 2. All right. Thanks for coming along and solving this with me. I'll see you tomorrow. Bye.